Hello there, and welcome to The Sleepless Scientist, a quiet place in the cosmos where your thoughts can unwind and knowledge becomes a soft lullaby for the night. Tonight's journey will take us into a question that sounds almost impossible at first. What if space and time themselves are not truly real in the way we imagine them? But before you settle in and get cozy, I'd love if you could take a moment to like this video and subscribe. Only if you truly find these quiet explorations enjoyable. And when you're ready, leave a comment to let me know where in the world you're listening from and what time it is for you right now. It's always such a joy to see all the places we gather from, each in our own little slice of time. Now feel free to dim the lights, maybe turn on a fan for a soft background hum, and let's gently begin our journey into the strange question of space and time together. And if your mind begins to wander, that's perfectly fine. Let it drift. We'll still be here, quietly unfolding the story. If you pause for a moment and look around the room you're in, space feels obvious. There's distance between you and the walls. There's space between objects on a table. There is room to move, to walk, to stretch your arms. Space seems like the invisible stage on which everything exists, and time feels just as natural. The quiet ticking of a clock, the steady rhythm of breathing, the slow passing of night toward morning. Time seems to flow forward, carrying everything with it moment by moment. Together, space and time feel like the most basic ingredients of reality. They feel so natural that it is difficult to imagine a universe without them. But physics has a curious habit of questioning the things that seem most obvious. Throughout the history of science, progress has often arrived when a deeply trusted intuition quietly fell apart. For thousands of years, people believed that Earth stood still at the center of the universe. The stars and planets appear to circle us each night, and the ground beneath our feet felt perfectly steady. The idea seemed completely reasonable, until careful observations revealed that Earth itself was moving. Later, another intuition began to crumble. Time, it was once believed, flowed the same for everyone everywhere. A second was a second, whether you were standing still or moving across the world. Yet early in the 20th century, Albert Einstein discovered something astonishing. Time does not pass at the same rate for everyone. When objects move extremely fast, time slows down for them compared to someone who remains still. Even gravity can stretch time. Clocks on satellites orbiting Earth tick slightly faster than clocks on the ground below. Engineers must account for this tiny difference when designing global navigation systems that guide airplanes and smartphones across the planet. Each of these discoveries quietly reshaped our understanding of reality. What once felt obvious turned out to be incomplete, and now physics may be approaching another moment like that. Some modern theories suggest that space and time themselves may not be the deepest layer of reality. Instead, they may emerge from something more fundamental, something deeper and more abstract. To understand why scientists are even considering such a strange possibility, it helps to think about how physics has traditionally described the universe. For centuries, physics treated space and time as the stage on which everything happens. Imagine a theatre stage. The stage itself remains still and unchanged, while actors move across it. In the same way, classical physics imagined a vast invisible stage called space. On this stage, planets orbit stars, apples fall from trees, and galaxies drift slowly through the darkness. Time, meanwhile, was imagined as a universal clock. No matter where you were in the universe, the clock ticked steadily forward, 1 second after another. Objects could move through space. Events could unfold through time. But the stage and the clock themselves were assumed to be fundamental. Yet as physicists looked deeper into the nature of the universe, this comfortable picture began to change. At extremely small scales, scales far smaller than atoms, our best theories begin to struggle. Distances become difficult to define. The smooth fabric of space-time that Einstein described may begin to behave in strange and unpredictable ways. Physicists call this unimaginably tiny scale the Planck length. It is roughly 10 to the minus 35 meters. To give a sense of how small that is, imagine shrinking an atom until it is the size of our entire solar system. Even then, the Planck length would still be far smaller than the nucleus at the center. At this scale, many physicists suspect that the familiar concept of space-time may dissolve into something deeper. Instead of space being a continuous expanse, it might emerge from networks of relationships between more fundamental elements of reality. Some ideas suggest that space-time could arise from patterns of quantum connections between particles. Others propose that the geometry of the universe might emerge from deeper mathematical structures. And some physicists wonder whether our experience of space and time might even depend partly on the way our brains organize information about the world around us. In other words, space and time might not be the foundation of reality. They might be the appearance that emerges from something else. This possibility can feel unsettling at first. After all, space is where we live. Time is what carries us through our lives. To imagine a universe without them seems almost impossible. But physics has taught us something important over the centuries. The universe does not always match the pictures that feel most intuitive to our minds. Sometimes reality is stranger and more beautiful than we expect. So tonight, we're going to take a slow and careful walk through the history of this idea. We'll explore how ancient philosophers first thought about space. We'll see how mathematics transformed our intuition about the universe. We'll meet Isaac Newton, who believed space and time were absolute and unchanging. And we'll encounter his rival, Gottfried Wilhelm Leibniz, who imagined a very different possibility, that space might simply be the relationship between objects. As the story unfolds, we'll see how Einstein reshaped our understanding of space-time, and how modern physics is beginning to ask an even deeper question. What if space and time are not the fundamental stage of reality at all? What if they are something that emerges from a deeper structure hidden beneath the surface of the universe? It's a strange thought. But as we'll soon discover, the path toward this idea began long ago, in the quiet reflections of ancient thinkers who were trying to understand the geometry of a triangle, and that is where our journey gently continues. If we travel far back in time, long before telescopes and particle accelerators, we find that people were already asking questions about space. Not about galaxies or black holes, of course, but about something quieter and closer to everyday life. The shapes of fields, the distances between cities, the angles of pyramids, the geometry of the world. In the ancient Mediterranean, particularly in Greece, mathematicians developed one of the most elegant intellectual achievements of early civilization: geometry. Geometry, quite literally, means earth measuring. It was originally a practical art used for dividing farmland, building structures, and navigating landscapes. But over time it became something deeper, a way of understanding patterns and relationships in space. One of the most famous figures in this story was Euclid, a mathematician who lived more than 2,000 years ago in the city of Alexandria. Euclid gathered together the mathematical knowledge of his time into a remarkable book called The Elements. For centuries it became one of the most influential scientific texts ever written. What makes Euclid's geometry so fascinating is that it describes shapes and distances without ever requiring the idea of an empty space that exists by itself. Instead, geometry was built entirely from relationships. Consider something very simple: a triangle. A triangle is defined by 3 straight lines that meet at 3 corners. Its properties come from the relationships between those lines, the lengths of the sides and the angles where they meet. If you know those relationships, You know the triangle. You do not need a background grid. You do not need coordinates. You do not need a vast invisible stage called space. The triangle exists through its internal structure. You can imagine drawing one in the sand, or carving one into stone, or even picturing one in your mind. The relationships remain the same. In fact, ancient geometry rarely described objects by their positions in a coordinate system the way we do today. When modern students learn geometry, they often draw shapes on graph paper. A pointer might have coordinates like 3,5, meaning 3 units along one axis and 5 units along another. But the Greeks did not think this way. They spoke about lines, intersections, ratios and angles. Their geometry was relational rather than coordinate-based. This difference might seem subtle at first, but it reflects a completely different way of thinking about space. In modern mathematics, it often feels natural to imagine a vast grid stretching endlessly in all directions. Every point in the universe could, in principle, be labelled with numbers along 3 axes: an x-axis, a y-axis, and a z-axis. But in the ancient world, this picture was far less common. Space was not automatically treated as a gigantic invisible container waiting to be filled with objects. Instead, geometry described how objects related to each other. Distances were distances between things. Angles were angles between lines. Shapes were structures defined by their internal relationships. If you think about it, this approach makes a lot of intuitive sense. Imagine you are standing in a quiet park at night. You see a tree to your left and a small pond to your right. You might describe their positions relative to yourself. The tree is about 20 steps away. The pond is perhaps 30 steps in the other direction. Your understanding of the space around you is relational. You're not thinking in terms of numerical coordinates. You're thinking about how things relate to one another. The ancient Greeks approached geometry in much the same spirit. Their mathematics captured relationships rather than absolute positions. Even their maps, which sometimes used early forms of latitude and longitude, did not yet create the modern habit of imagining space as a fully gridded numerical structure. The world was a landscape of relationships rather than a mathematical grid. This way of thinking extended beyond mathematics into philosophy. Many early thinkers believed that empty space containing absolutely nothing, might not even exist. For example, Aristotle argued that nature abhors a vacuum. According to this view, true emptiness was impossible. Space only existed where matter existed. While modern physics no longer accepts Aristotle's reasoning, his intuition reflects the broader mindset of the ancient world. Space was not treated as a physical substance. It was simply the way objects were arranged relative to each other. If all objects disappeared, the very idea of space might disappear as well. This relational perspective dominated much of early thinking about the universe, and in some ways, it remains surprisingly close to everyday experience. After all, when we move through our homes or walk through a city, we rarely think about invisible coordinate axes. We think about doors and hallways, streets and intersections, distances and directions. Space is experienced through relationships. Yet this ancient viewpoint would eventually change. During the scientific revolution of the 17th century, a new mathematical tool began to spread through Europe. It allowed mathematicians to connect numbers and shapes in a powerful new way. With this invention, every point in space could be described using simple numerical coordinates. The world could be mapped onto a grid. This idea may sound completely ordinary today. It is taught in classrooms around the world and used in everything from computer graphics to satellite navigation. But when it first appeared, it transformed the way people imagined space. Suddenly space began to look less like a web of relationships and more like an enormous numerical canvas. A quiet conceptual shift had begun. And at the centre of that shift was a French philosopher and mathematician named René Descartes. His work would open the door to a new way of imagining the universe, one where space itself might begin to feel like a real and independent thing. For many centuries, the relational way of thinking about space worked perfectly well. Geometry described shapes, architecture relied on angles and proportions, and navigation used distances and directions between known places. But during the 17th century, something quietly transformative happened in mathematics. A French philosopher and mathematician named René Descartes introduced a new way to connect numbers and geometry. At first glance, the idea seems simple. Imagine placing a sheet of graph paper on a table. The paper contains two lines that cross at right angles in the centre. One line runs horizontally and the other runs vertically. The horizontal line is called the x-axis. The vertical line is called the y-axis. Now imagine that every point on the paper can be described using two numbers. The first number tells you how far to move along the x-axis. The second number tells you how far to move along the y-axis. For example, a point might lie at 3 units along the x-axis and 4 units along the y-axis. In everyday mathematical language, this might be written as the point 3, 4. But when spoken aloud in a calm narrative voice, it is simply the location that lies 3 units across and 4 units upward from the centre. With this system, shapes could suddenly be described using numbers. A curve could be drawn by following a mathematical rule. A straight line could be represented by a simple relationship between the numbers along the axes. This connection between numbers and shapes opened an entirely new world of mathematical possibilities. Today, this system is known as the Cartesian coordinate system, named after Descartes himself. It is now so familiar that we rarely stop to think about how revolutionary it once was. Before Descartes, geometry and algebra were largely separate, branches of mathematics. Geometry studied shapes and figures, algebra studied numbers and equations. The coordinate system allowed the two to merge. A mathematical rule could now produce a shape. A shape could now be described by an equation. For example, imagine a rule that says, as one number increases, another number increases in the same steady way. If you plot all the points that follow that rule on the coordinate grid, they form a straight line. More complicated rules produce curves, waves, spirals, and countless other patterns. Suddenly mathematics could paint pictures. And just as importantly, pictures could describe mathematics. This was an extraordinary breakthrough, but something else happened at the same time, something subtle, almost psychological. When you place objects on a coordinate grid, space begins to look like a vast sheet of graph paper. Every point has coordinates. Every location can be labelled with numbers. It becomes easy to imagine that space itself is nothing more than an enormous grid stretching endlessly in all directions. Of course, Descartes himself didn't necessarily intend this interpretation. In fact, he believed something quite different. Descartes argued that space could not exist without matter. In his view, what we call space was simply the extension of physical substance. Where matter existed, space existed. Where there was no matter, there was no space. In other words, Descartes rejected the idea of truly empty space. This idea echoed some earlier philosophical traditions, including certain views of Plato and Aristotle. Yet even though Descartes himself did not believe in empty space, the coordinate system he created had an unexpected effect on the imagination of later scientists. Because the grid allowed space to be described numerically, it became tempting to think of space as something independent of the objects within it. The coordinate grid created a powerful visual metaphor. Space began to look like a stage that already existed waiting for objects to move across it. You can imagine it like a giant sheet of graph paper extending far beyond the edges of the universe. Planets, stars, and galaxies could be placed on this sheet using coordinates. Their motion could be tracked by watching how those coordinates changed over a time. This mathematical picture would soon become the foundation for one of the most influential scientific frameworks in history, the work of Isaac Newton. Newton adopted the coordinate-based description of space and combined it with his laws of motion and gravity. Using this mathematical framework, he could calculate the paths of planets, the fall of objects on Earth, and even the motion of comets across the sky. Newton's equations were astonishingly successful. They could predict celestial events with incredible precision. They explained the motion of the moon, the tides of the oceans, and the paths of cannonballs fired across a battlefield. Because Newton's system worked so well, many scientists began to take the coordinate grid more seriously than ever before. What if the grid was not merely a mathematical tool? What if it represented something real? What if space itself was a genuine structure, a kind of invisible framework underlying the universe? In Newton's view, that is exactly what space was, an absolute stage on which all motion occurred. But this interpretation raised an important philosophical question. Is the grid truly part of the universe? Or is it simply a convenient language invented by mathematicians? When you draw a graph on paper, the grid does not exist inside the curve you draw. The grid is merely a way to describe the curve. Perhaps the coordinate grid used in physics is similar. Perhaps it's a map rather than the territory itself. This distinction would become one of the central debates in the philosophy of space and time. And as the story continues, that debate would grow into a famous intellectual rivalry between two remarkable thinkers. On one side stood Isaac Newton, convinced that space and time were real and absolute. On the other stood a brilliant German mathematician named Gottfried Wilhelm Leibniz, who believed that space might be nothing more than relationships between objects. Their disagreement would shape centuries of scientific thought. And the echoes of that debate still resonate today, as modern physics once again begins to ask whether the stage of the universe is truly fundamental, or merely a convenient way of describing something deeper. By the late 17th century, the coordinate grid had quietly reshaped the mathematical imagination of Europe. With this new tool in hand, scientists could now describe motion with remarkable clarity. Paths through space could be written as numerical relationships. Positions could be tracked using coordinates along the x-axis, the y-axis, and the z-axis. But it was Isaac Newton who turned these mathematical tools into a complete description of motion. Newton lived during a time when astronomy was rapidly advancing. Observations of planets, moons, and comets were becoming increasingly precise. The motions of these celestial bodies followed patterns that begged for explanation. Why did planets trace graceful paths around the sun? Why did the moon orbit the Earth? Why did objects fall toward the ground? Newton answered these questions with a set of mathematical laws that remain among the most powerful ideas ever developed in science. His laws of motion described how objects change their motion when forces act upon them, and his law of gravity explained that every object in the universe attracts every other object through a force that depends on their masses and the distance between them. With these principles, Newton was able to calculate the motion of planets with extraordinary accuracy, the orbit of the moon, the path of a falling apple, the trajectory of a comet passing through the solar system. All could be predicted using the same set of mathematical rules. To make these calculations work, Newton relied heavily on the coordinate framework introduced by Descartes. Objects moved along paths described by changing positions in space, and time flowed steadily forward as those positions changed. But Newton went further than simply using coordinates as a mathematical tool. He believed that space itself was real. To Newton, space was not just a convenient way to describe motion. It was a genuine feature of the universe, a vast invisible arena in which everything existed. Imagine once again the theatre stage we mentioned earlier. In Newton's universe, the stage exists whether or not actors are present. Even if every star and planet vanished, space itself would remain. It would still stretch endlessly in every direction. Newton called this idea absolute space. According to this view, every object in the universe has a position relative to this underlying structure. Even if we cannot measure that position directly, it still exists. Similarly, Newton believed in absolute time. Time, in his view, flows steadily and uniformly everywhere in the universe. It does not depend on events. It does not depend on observers. It simply moves forward, second after second, like a perfectly reliable cosmic clock. This idea was quite different from earlier philosophical views. In many ancient traditions, time was often described as the measurement of change. If nothing changed, time would have no meaning. But Newton imagined time as something deeper. Even if the entire universe were frozen in perfect stillness, Newton believed that time would continue to flow. A silent clock would keep ticking in the background. This notion of absolute time felt natural within Newton's system because it allowed his equations to describe motion with remarkable consistency. Objects move through space as time advances. Positions change, velocities change. For example, if an object moves with constant velocity, its position changes steadily over time. If we were to draw its motion on a graph, with time running along the horizontal direction and position along the vertical direction, the path would form a straight line. When forces act, the line bends. Acceleration changes the slope of that path. In this way, the geometry of motion could be visualized within the coordinate grid. Space provided the framework for position. Time provided the framework for change, and together they formed the stage on which all of Newtonian physics unfolded. Newton also believed that there was something called absolute rest. Imagine a coordinate system whose axes remain perfectly still relative to the universe itself. If an object remained fixed relative to those axes, it would be truly motionless. Of course, identifying such a reference frame is not easy. On Earth, everything moves. The planet rotates on its axis. It orbits the Sun. The Sun itself moves around the centre of the Milky Way, galaxy, and the galaxy drifts through the wider universe. So in practice, scientists measure motion relative to nearby objects. But Newton believed that beneath all these relative motions, there still existed an ultimate reference frame of true rest, even if we could never observe it directly. This idea stood in tension with an earlier insight from Galileo. Galileo had shown that motion is relative. If you are sitting on a smoothly moving ship and you toss a ball upward, the ball falls back into your hand just as it would if the ship were standing still. Inside the cabin, the laws of physics behave the same. There is no experiment you can perform that reveals whether the ship is moving steadily or resting. This principle became known as Galilean relativity. Newton accepted the mathematics of this principle, but he believed that the universe still possessed an underlying structure of absolute space and absolute time. The success of Newton's physics made this picture extremely persuasive. For more than 2 centuries, scientists used Newton's framework to describe everything from the motion of planets to the behaviour of projectiles. The universe appeared to operate like a vast, perfectly organised machine. Space provided the stage, time provided the rhythm, and the laws of motion described the choreography of everything that existed. But even during Newton's lifetime, not everyone was convinced. One particularly sharp critic believed that Newton's idea of absolute space was unnecessary. To this thinker, space was not a container holding objects. Instead, it was nothing more than the relationships between those objects. This critic was a mathematician, philosopher, and diplomat whose intellect rivaled Newton's own. His name was Gottfried Wilhelm Leibniz, and his disagreement with Newton would become one of the most famous debates in the history of science. It was a debate about something that still puzzles physicists today. Is space a real thing, or is it simply the pattern of relationships between the objects in the universe? As we'll soon see, the answer to that question may be far stranger than either Newton or Leibniz could have imagined. While Isaac Newton imagined the universe unfolding on a vast invisible stage of absolute space and steady time, another brilliant thinker saw the situation very differently. His name was Gottfried Wilhelm Leibniz. Leibniz was one of the great polymaths of the 17th century. He worked as a mathematician, philosopher, diplomat, engineer, and historian. Like Newton, he independently invented calculus, one of the most powerful mathematical tools ever created. But when it came to the nature of space and time, Leibniz did not agree with Newton at all. To understand his argument, it helps to imagine a simple situation. Picture two identical universes. In both universes, there are the same stars, the same planets, and the same distances between them. Every relationship between objects is exactly the same. The only difference is that the entire second universe has been shifted a few kilometers to the left relative to Newton's absolute space. Nothing else has changed. The stars remain the same distance from each other. The planets orbit in exactly the same way. The laws of physics behave identically. According to Newton's view, these two universes would still be different. In the first universe, the stars occupy one region of absolute space. In the second universe, they occupy a slightly different region. But Leibniz asked a simple question. If absolutely no observable difference exists between the two universes, in what sense can they truly be different? Leibniz believed this scenario revealed a problem with the idea of absolute space. If space were truly an independent structure of the universe, then shifting everything together should create a new physical situation. Yet nothing observable would change. For Leibniz, this suggested that absolute space might not exist at all. Instead, he proposed something far simpler. Space is nothing more than the pattern of relationships between objects. When we say that two stars are separated by a certain distance, we are describing a relationship between them. When we say that one planet lies between two others, we are describing another relationship. But these relationships do not require a background grid. They only require objects interacting with one another. In Leibniz's view, if the entire universe were shifted together, the relationships between objects would remain identical, and therefore the universe itself would remain exactly the same. There would be no meaningful difference. This way of thinking became known as the relational view of space. Space is not a container. It is a network of relationships, a bit like a web. Imagine a spider's web stretched between branches of a tree. If you remove the branches, the web collapses. The web cannot exist independently. Its structure is defined entirely by the connections between its threads. Leibniz believes space might be similar. Without objects, there is no space. There are only relationships. Leibniz applied the same reasoning to time. Newton had argued that time flows independently of events, a cosmic clock ticking in the background. But Leibniz suggested something quite different. Perhaps time is simply the ordering of events. When one event happens before another, we say time has passed. But without events, the concept of time may lose its meaning. In other words, time might not exist independently of change. Instead, time could simply be the structure of change itself. This view has a certain intuitive appeal. After all, When we measure time in everyday life, we almost always rely on change. The movement of clock hands, the oscillation of atoms in an atomic clock, the rising and setting of the sun. Without change, it becomes difficult to define what we mean by time passing. Leibniz believed that both space and time should be understood in this relational way. They are not things, they are patterns. Patterns describing how objects relate to one another, patterns describing how events follow one another. To many philosophers, this idea seemed elegant and economical. It removed the need for an invisible structure called absolute space. But it also raised an important challenge. If space is only relationships between objects, how do we explain motion? For example, imagine a spinning object, a rotating bucket of water, for instance. As the bucket spins, the water inside climbs up the sides of the container, forming a curved surface. Newton used this example to argue that rotation must be measured relative to absolute space. Otherwise, how could the water know that it is spinning? Leibniz was not fully convinced by this argument. He believed that motion could ultimately be explained by relationships between objects and their interactions. This debate between Newton and Leibniz became one of the most famous intellectual disputes in the history of science. Neither side fully resolved the issue, and for centuries physicists continued to use Newton's framework because it worked so well. The equations predicted planetary motion with astonishing precision. They guided navigation across oceans. They helped engineers design bridges, cannons, and machines. In practical terms, Newton's picture of absolute space and time seemed undeniable. But the philosophical questions raised by Leibniz never completely disappeared. His relational view continued to linger quietly in the background of scientific thought. And as the centuries passed, new discoveries would slowly reopen the debate. By the 19th century, scientists would encounter a phenomenon that seemed to fill space itself with invisible energy, a phenomenon known as the electromagnetic field. And this discovery would once again reshape humanity's understanding of what space might truly be. During the long intellectual disagreement between Isaac Newton and Gottfried Wilhelm Leibniz, one particular thought experiment became especially famous. It involved nothing more complicated than a bucket of water. At first glance, it sounds almost too simple to matter. Yet this humble bucket would become one of the most discussed examples in the philosophy of physics. Imagine a wooden bucket hanging from a rope. The bucket is filled with water. Initially, everything is perfectly still. The rope hangs straight down. The bucket does not move. The water inside is calm and flat, forming a smooth horizontal surface. Now imagine twisting the rope tightly and letting go. The bucket begins to spin. At first, something interesting happens. The bucket starts rotating, but the water inside does not immediately follow. For a short moment, the water remains almost still, while the wooden walls of the bucket spin around it. During this brief stage, the surface of the water remains flat. But as the bucket continues spinning, friction between the bucket and the water gradually pulls the water along. The water begins to rotate as well, and once the water is fully spinning with the bucket, its surface changes shape. Instead of remaining flat, the water climbs slightly up the sides of the bucket. The center dips downward, forming a shallow, curved surface. If you looked carefully, the surface would resemble a gentle bowl. This curved surface puzzled Newton. Why would the water climb the walls of the bucket? The most natural explanation is that the spinning motion creates a force that pushes the water outward. Today, we call this effect centrifugal force. But Newton wanted to understand something deeper. Relative to what is the water spinning? At first, when the bucket rotates but the water does not, there is clear relative motion between them. The bucket moves relative to the water, yet the water's surface remains flat. Later, when the water begins spinning, Together with the bucket, there is almost no relative motion between them. Both rotate at the same speed. Yet this is precisely when the surface becomes curved. This observation led Newton to a striking conclusion. The curved surface cannot depend on motion relative to the bucket. Because when the water and bucket move together, there is no relative motion between them. Yet the curved surface still appears. Therefore, Newton argued, the water must be rotating relative to something else, something deeper, something not visible. He concluded that the rotation must be measured relative to absolute space. In Newton's view, the water knows it is spinning because it is rotating relative to the fixed background structure of the universe. Absolute space acts like an invisible reference frame. Even if we cannot see it directly, it provides the standard against which true motion can be measured. This argument seemed powerful. After all, the curved water surface is a real physical effect. It must have some cause. If it cannot be explained by motion relative to nearby objects, perhaps it must be explained by motion relative to the structure of space itself. For many scientists, this example reinforced Newton's belief that space was more than just relationships between objects. Space appeared to have its own physical significance, but supporters of Leibniz were not entirely convinced. They suggested that the rotating bucket experiment might still be explained without invoking absolute space. Perhaps the important reference was not space itself, but the rest of the universe. Imagine the distant stars scattered across the night sky. From Earth, these stars appear almost motionless, forming a vast cosmic backdrop. If the bucket rotates relative to those distant stars, perhaps that rotation could explain the curved water surface. In this interpretation, rotation would not be measured relative to empty space. Instead, it would be measured relative to the distribution of matter throughout the universe. This idea would later influence a principle associated with the physicist Ernst Mach. Mach proposed that inertia, the resistance objects have to changes in motion, might arise from interactions with the mass of the entire universe. In other words, the behavior of the water in the spinning bucket might depend on the presence of all the distant stars and galaxies. The bucket experiment therefore raised a deeper question than Newton had intended. What determines motion? Is motion measured relative to a fixed background called space? Or is motion defined by relationships between objects across the entire universe? For centuries, physicists debated this question. Newton's framework worked extraordinarily well in practice. His laws of motion predicted planetary orbits, tides, and falling objects with astonishing accuracy. Because of this success, most scientists adopted Newton's picture of absolute space and time, yet the philosophical discomfort remained. Newton's invisible stage seemed strangely difficult to observe. Absolute space could never be measured directly. It was a concept inferred from the behavior of motion. Meanwhile, the relational idea of Leibniz continued to whisper quietly in the background of physics. Perhaps space was not an object. Perhaps it was simply the structure formed by relationships between matter. For a long time, this question remained unresolved. But as the 19th century unfolded, a new discovery would change the discussion once again. Scientists began to realize that something invisible seemed to fill the universe. Not matter, not particles, but something capable of carrying energy and motion across empty space. This mysterious phenomenon was called the electromagnetic field, and it would soon transform humanity's understanding of what space itself might contain. For more than 200 years, Isaac Newton's picture of the universe worked astonishingly well. Planets moved according to predictable paths. Comets returned on schedule. Objects fell to the ground exactly as Newton's equations predicted. Within this framework, space behaved like a quiet stage. Objects moved across it. Forces acted between them. But the stage itself remained passive. Empty space, in Newton's view, did nothing. It simply existed. Yet during the 19th century, a series of discoveries began to challenge this comfortable picture. The story begins with something very familiar to us today: electricity and magnetism. People had known about these phenomena for centuries. Ancient Greek philosophers noticed that rubbing amber with cloth could attract small bits of dust. Lodestones, a naturally magnetic mineral, were known to pull iron toward them. But these effects seemed mysterious and unrelated. Electricity appeared in sparks. Magnetism appeared in certain minerals. No one yet understood that they were deeply connected. Then, in the early 19th century, scientists began discovering surprising links between the two. In 1820, the Danish physicist Hans Christian Ørsted performed a simple but remarkable experiment. While working with electric currents, he noticed that a nearby compass needle suddenly deflected. The compass, which normally points toward Earth's magnetic north, changed direction whenever electricity flowed through a wire. This discovery revealed something extraordinary. Electric currents create magnetic effects. Electricity and magnetism were not separate phenomena after all. They were connected. Over the following decades, several scientists, including André-Marie Ampère and Michael Faraday, began exploring this relationship more deeply. Faraday in particular introduced a powerful new way of thinking about forces. Before Faraday, forces were often imagined as acting directly across empty space. For example, Newton's gravity seemed to pull objects toward each other even when nothing existed between them. This idea sometimes made scientists uncomfortable. How could one object influence another across empty space? Faraday proposed a different picture. Instead of imagining forces leaping instantly from one object to another, he suggested that objects create something around themselves, something invisible, something that fills the surrounding space. He called this something a field. A field describes how the influence of an object spreads through the region around it. For example, a charged particle creates an electric field. Another charged particle entering that field will feel a force. Similarly, a magnet creates a magnetic field. Iron filings placed nearby align themselves along graceful curved lines, revealing the structure of the field. Faraday often visualized these patterns as lines of force stretching through space. Imagine delicate threads woven through the air. Each thread marks the direction in which a small test particle would be pushed. These lines are not physical wires. They're simply a way of visualizing the structure of the field. But the idea was powerful. It suggested that space itself could contain physical properties, even when no particles were present. This concept took an enormous leap forward in the 1860s, when the Scottish physicist James Clerk Maxwell translated Faraday's intuitive ideas into mathematics. Maxwell developed a set of equations describing how electric and magnetic fields behave and interact. These equations revealed something astonishing. Changing electric fields produce magnetic fields. Changing magnetic fields produce electric fields. And when these changes propagate through space together, they form waves, electromagnetic waves. These waves travel through space at a specific speed. When Maxwell calculated this speed using the constants in his equations, he obtained a number astonishingly close to the measured speed of light. This led Maxwell to a breathtaking conclusion. Light itself is an electromagnetic wave. In other words, the light reaching your eyes from a distant star is not a stream of particles flying through empty space. It is a ripple moving through electromagnetic fields, a kind of vibration traveling across the invisible structure filling the universe. Suddenly, space did not seem so empty anymore. Even regions containing no matter could still contain fields, and those fields could carry energy, momentum, and waves across enormous distances. Radio waves, visible light, X-rays. All are forms of electromagnetic radiation travelling through these fields. This discovery raised a fascinating question. If waves are moving through space, what exactly are they moving through? Ocean waves travel through water. Sound waves travel through air. What medium carries electromagnetic waves? Many 19th century scientists proposed that space might be filled with an invisible substance called the luminiferous ether. This hypothetical ether would act as the medium through which light waves propagate. But despite many careful experiments, scientists could never detect this ether directly. The most famous attempt was the Michelson-Morley experiment in 1887. Researchers tried to measure the motion of Earth through this invisible ether by comparing the speed of light in different directions. If Earth were moving through the ether, light travelling along the direction of motion should behave slightly differently from light travelling across it. Yet the experiment found no such difference. No matter how carefully scientists measured, the speed of light appeared identical in all directions. The ether seemed impossible to detect. This puzzling result would soon create a crisis in physics, because if electromagnetic waves do not travel through a medium, what exactly are they moving through? What is waving? What is vibrating? The answer to this mystery would eventually lead to one of the greatest revolutions in scientific thought. A revolution led by a young patent clerk named Albert Einstein. And with Einstein's work, the entire idea of space and time would begin to change once again. As scientists in the 19th century absorbed the implications of Maxwell's work, a strange question began to circulate through laboratories and lecture halls. If light is a wave, what exactly is waving? For centuries, waves had always required something to move through. Ocean waves travel through water. Sound waves move through air. Even waves on a rope require the rope itself to vibrate. So when Maxwell's equations revealed that light is an electromagnetic wave travelling through space, physicists naturally assumed that space must contain some kind of medium. This invisible substance was given a poetic name, the luminiferous ether. The word ether suggested something subtle and delicate, an invisible fabric filling the cosmos. According to this idea, the ether would exist everywhere. It would fill the gaps between atoms. It would stretch across the enormous emptiness between stars. And it would act as the medium through which electromagnetic waves travel. In this picture, when light moves through space, it is really a ripple passing through this universal ether. At first, the idea seemed quite reasonable. After all, it solved the problem of waves needing a medium. But the ether also raised some puzzling questions. For example, if the ether filled all of space, the Earth should be moving through it as our planet travels around the Sun. This motion should create something similar to a cosmic wind. Imagine riding a bicycle on a calm day. When the bicycle begins moving, the air starts flowing past your face. The faster you ride, the stronger the wind feels. Scientists expected that a similar effect might occur as Earth moves through the ether. If the planet travels through this invisible medium, there should be an ether wind blowing past the Earth. And this ether wind should affect the speed of light, depending on the direction in which the light travels. Light moving against the ether wind should behave slightly differently from light moving across it. By measuring these tiny differences, scientists hoped they could detect the motion of Earth through the ether. In the late 19th century, two physicists named Albert Michelson and Edward Morley designed an extraordinarily precise experiment to search for this effect. Their instrument used a device called an interferometer. The idea behind the experiment was subtle but elegant. A beam of light would be split into two identical beams. One beam would travel in one direction. The other beam would travel in a direction perpendicular to the first. After travelling their separate paths, the two beams would reunite and interfere with each other. If one beam had taken slightly longer to complete its journey than the other, the interference pattern would shift. Even incredibly tiny differences in travel time could be detected, Michelson, and Morley reasoned that if the Earth were moving through the ether, light travelling along the direction of that motion should take a slightly different time to return than light travelling across it. Their experiment was sensitive enough to detect differences far smaller than a fraction of a billionth of a second. The expectation was clear: a shift in the interference pattern should appear. But when the experiment was performed in 1887, the result was astonishing. Nothing happened. No shift appeared. No evidence of an ether wind could be detected. The speed of light appeared to be exactly the same in every direction. Michelson and Morley repeated the experiment again and again, rotating the apparatus and performing measurements at different times of year as Earth moved through its orbit. Still nothing changed. The speed of light remained constant. For many physicists, this result was deeply unsettling. If the ether existed, Earth's motion through it should have been detectable. Yet, the experiment stubbornly refused to reveal any sign of such a medium. Some scientists attempted to rescue the ether theory by proposing increasingly complicated explanations. Perhaps the ether was dragged along by Earth. Perhaps the measuring instruments themselves changed length as they moved through the ether. These ideas grew more and more elaborate, yet none provided a truly satisfying explanation. Meanwhile, Maxwell's equations continued to describe electromagnetic phenomena with stunning accuracy. And those equations predicted that electromagnetic waves travel at a specific speed. The speed we call the speed of light. In modern units, this speed is about 300,000 kilometers per second, or, expressed another way, about 300 million meters per second. In spoken language, we might describe it simply as light, travelling 300,000 kilometers every second. This number appeared again and again in experiments. No matter how carefully scientists measured it, the speed of light remained the same. The failure to detect the ether created a growing sense that something fundamental about space and motion had been misunderstood. Perhaps the problem was not with the experiments. Perhaps the problem lay deeper in the assumptions about space and time themselves. At the beginning of the 20th century, a young physicist began to think about this mystery from a completely new perspective. His name was Albert Einstein. Instead of trying to explain why the ether could not be detected, Einstein asked a simpler question. What if the ether does not exist at all? What if the speed of light is truly the same for every observer, no matter how they move? If that idea were true, it would require a radical rethinking of both space and time. Distances might change depending on motion. Clocks might tick at different rates depending on speed. Space and time might not be separate things at all. They might form a single unified structure. Structure that would soon be called spacetime. And with this idea, the comfortable Newtonian stage of absolute space and absolute time would begin to dissolve into something far stranger and far more beautiful. At the beginning of the 20th century, physics stood at a strange crossroads. On one side stood Newton's universe, steady, predictable, and elegant. Space was an infant stage. Time flowed like a perfectly reliable clock. Objects moved according to precise mathematical laws. On the other side stood Maxwell's theory of electromagnetism. Its equations described electric and magnetic fields with remarkable accuracy. But hidden within those equations was a curious feature. They predicted that electromagnetic waves always travel at one specific speed, the speed of light. In everyday language, this speed is about 300,000 kilometers every second, or roughly 300 million meters per second. No matter how scientists measured it, the result remained the same. Light always traveled at this exact speed. At first, physicists tried to explain this constant speed using the idea of the ether, but as we have seen, the ether stubbornly refused to appear in experiments. By the year 1905, the situation had become increasingly puzzling. That year, a young physicist working at a patent office in Switzerland began thinking deeply about this problem. His name was Albert Einstein. Einstein was fascinated by a simple but powerful question. What would happen if someone could travel alongside a beam of light? Imagine chasing a pulse of light through space at the same speed that the light itself travels. According to classical physics, you might expect the light wave to appear frozen, just as ocean waves appear stationary if you move along with them. But Maxwell's equations did not allow this. They predicted that light always moves at the same speed, no matter how fast the observer is moving. Einstein realized that if this principle were true, then something much deeper must be happening. The rules governing space and time themselves must change. In 1905, Einstein proposed two simple ideas. First, the laws of physics are the same for all observers who move at constant speed relative to one another. Second, the speed of light in empty space is always the same for every observer, no matter how fast that observer is moving. These two principles may sound modest, but their consequences were astonishing. Imagine two observers moving relative to one another. One observer stands on a platform, another observer rides inside a fast-moving train. If a flash of light appears inside the train, both observers will measure that light travelling at exactly the same speed, even though the train itself is moving. For this to be true, space and time must behave in ways that defy our everyday intuition. Lengths can shrink, clocks can slow down. Events that appear simultaneous to one observer may occur at different times for another. These effects are not illusions. They are real features of how space and time behave at high speeds. One of the most famous consequences of Einstein's theory is time dilation. Imagine a clock travelling inside a fast-moving spacecraft. From the perspective of someone standing on Earth, that clock will tick more slowly. Time itself appears to stretch. The faster the spacecraft moves, the more pronounced this effect becomes. Another consequence is length contraction. Objects moving at extremely high speeds appear slightly shortened along the direction of motion. To the traveller inside the spacecraft, nothing unusual occurs. Their own clock ticks normally. Their measuring rods retain their usual lengths. But observers in different states of motion disagree about distances and durations. This strange behaviour arises because space and time are not independent. They are woven together. In Einstein's new picture, space and time form a single four-dimensional structure. Physicists call this structure spacetime. To visualize this idea, imagine a map. On a typical map, positions are described using two directions, north and south, east and west. To describe motion through spacetime, we need one additional direction: time. Instead of using only three coordinates, x, y, and z, we now describe events using four coordinates, three directions of space, and one direction of time. In spoken form, we might describe an event as occurring at a certain place in space and at a certain moment in time. Together, these coordinates locate the event within space-time. Every event in the universe can be described in this way: the birth of a star, the collision of two galaxies, or the quiet ticking of a clock in a small room on Earth. All are points within space-time. Einstein's theory showed that different observers slice this space-time differently. Each observer divides space-time into their own versions of space and time, yet the deeper structure, the space-time itself, remains consistent. One particularly elegant consequence of special relativity connects energy and mass. Einstein discovered that mass and energy are related by a simple relationship. In spoken language, we often say it as energy equals mass times the speed of light squared. This means that even a tiny amount of mass contains an enormous amount of energy. The speed of light multiplied by itself is an enormous number. So when mass is converted into energy, the result can be extremely powerful. This relationship plays an important role in nuclear reactions and in the energy produced by stars. But beyond its practical implications, the deeper lesson of Einstein's work was philosophical. Space and time were no longer rigid, independent entities. They had become flexible aspects of a deeper structure, spacetime. And this realization set the stage for Einstein's next great leap, a theory in which gravity itself would turn out to be a property of spacetime geometry, a theory that would reveal that massive objects do not simply move through space, they reshape it. After publishing his theory of special relativity in 1905, Albert Einstein knew something important was still missing. Special relativity worked beautifully for objects moving at constant speeds. It described how clocks slow down and how lengths contract when motion approaches the speed of light. But it had not yet explained gravity. Newton's theory of gravity had worked remarkably well for more than 2 centuries. According to Newton, gravity is a force. Every object with mass pulls on every other object. The strength of this attraction depends on 2 things: the masses of the objects and the distance between them. In everyday language, we often say that the gravitational force becomes weaker as objects move farther apart. Newton's equations predicted the motion of planets with extraordinary precision. They explained why the Moon orbits Earth, why Earth orbits the Sun, and why comets travel along long elliptical paths through the solar system. Yet there was something about Newton's theory that bothered Einstein. In Newton's picture, gravity acts instantly across space. If the Sun were to suddenly move, the Earth would feel that change immediately. No delay. But special relativity had introduced a new principle. Nothing can travel faster than the speed of light. If information about motion cannot move faster than light, how can gravity act instantly across enormous distances? Einstein believed the answer required a completely new understanding of gravity. The breakthrough came from a simple observation about falling objects. Imagine standing inside an elevator. If the elevator cable suddenly snaps and the cabin begins falling freely toward the ground, something strange happens. Inside the elevator, everything appears weightless. A coin released from your hand would float beside you. A drop of water would hover in the air. For a brief moment, gravity would seem to disappear. Einstein realized that falling freely under gravity feels exactly the same as floating in empty space. This insight became known as the equivalence principle. It suggests that gravity and acceleration are deeply connected. To see this more clearly, imagine another elevator. This one is drifting far out in space, far from any planets or stars. There is no gravity. Now imagine rockets attached to the elevator suddenly fire. The cabin begins accelerating upward. From inside the elevator, the floor would press against your feet. Objects dropped from your hand would fall toward the floor. It would feel exactly like gravity. Yet in this case, the effect comes from acceleration. Einstein realized that these 2 situations, gravity and acceleration, are fundamentally similar. From this idea, he began building a new theory of gravity, a theory that would no longer treat gravity as a force acting through space. Instead, gravity would emerge from the geometry of space-time itself. To picture this idea, physicists often use a simple analogy. Imagine a large flexible sheet stretched tightly in all directions. Now place a heavy bowling ball in the center of the sheet. The sheet bends under the ball's weight, forming a curved depression. If you roll a smaller marble across the sheet, the marble's path will curve as it moves near the bowling ball. The marble is not being pulled by a mysterious force. It is simply following the curved surface of the sheet. Einstein proposed that something similar happens in the universe. Mass and energy bend space-time. Planets, stars, and galaxies distort the geometry around them. objects moving through this curved space-time follow paths determined by that geometry. These paths are called geodesics. In spoken language, we might describe them simply as the natural paths objects follow through curved space-time. From this perspective, gravity is not really a force. It is the result of space-time curvature. The Earth orbits the Sun because space-time around the Sun is curved. The Moon orbits Earth for the same reason. Even light, which has no mass, follows these curved paths. When light passes near a massive object, its path bends. This effect is called gravitational lensing. Astronomers have observed it many times. Light from distant galaxies bends around massive clusters of galaxies, producing arcs and distorted images in the sky. Einstein's theory of general relativity, published in 1915, described these effects with remarkable accuracy. It explained small anomalies in the orbit of Mercury that Newton's equations could not fully account for. It predicted that time itself flows more slowly near massive objects. Clocks closer to Earth's surface tick slightly more slowly than clocks in orbit. Even modern navigation systems must account for this effect. Satellites carrying atomic clocks experience slightly different gravitational conditions than clocks on Earth. Without corrections from general relativity, global positioning systems would drift by kilometers within a single day. Perhaps most astonishing of all, general relativity predicted the existence of gravitational waves. These are ripples in space-time itself. When massive objects such as black holes collide, they create waves that spread outward through the fabric of space-time. In 2015, scientists using the LIGO observatory detected these waves for the first time, a discovery confirming Einstein's prediction 100 years after the theory was first proposed. With general relativity, Einstein had accomplished something extraordinary. Space and time were no longer passive stages. They had become dynamic participants in the universe. They could bend, they could stretch, they could ripple like the surface of a cosmic ocean. Yet even Einstein suspected that this theory might not be the final answer, because deep within the smaller scales of nature something strange begins to happen. And in that strange domain, the smooth fabric of space-time may start to unravel. After Einstein revealed that gravity is the curvature of space-time, the universe began to look like an elegant geometric structure. Mass bends space-time. Planets follow curved paths through that geometry. Light itself can bend as it travels past massive objects. For many decades, this picture worked astonishingly well. General relativity successfully described black holes, gravitational waves, and the expansion of the universe. Yet physicists eventually realized something troubling. Einstein's theory assumes that space-time is smooth, continuous, infinitely divisible. In principle, you could zoom in on space-time forever and still find a smooth surface, much like zooming in on a perfectly polished marble table. But another theory of nature tells a very different story. Quantum mechanics, quantum physics, describes the behavior of matter and energy at extremely small scales. Atoms, electrons, and particles even smaller than those. And in the quantum world, smoothness often disappears. Instead, nature becomes restless, uncertain, full of tiny fluctuations. To understand why this matters, imagine zooming in closer and closer on space-time itself, closer than atoms, closer than the nuclei of atoms, closer even than the smallest particles we have detected. Eventually, physicists suspect that we would reach a scale so small that our usual ideas of space and time begin to break down. This scale is known as the Planck scale. The Planck scale is named after the German physicist Max Planck, who helped lay the foundations of quantum theory at the beginning of the 20th century. Planck discovered that certain physical quantities can be combined to produce natural units of measurement. These units describe scales where gravity and quantum physics should become equally important. One of these units is the Planck length. In spoken form, the Planck length is about 1.6 times 10 to the minus 35 meters. That number is unimaginably small. To appreciate just how tiny it is, consider this comparison. An atom is already extremely small, but the Planck length is about 20 orders of magnitude smaller than an atomic nucleus. If an atom were magnified to the size of the observable universe, the Planck length would still be smaller than a grain of sand. Another important unit is the Planck time. The Planck time describes how long it takes light to travel one Planck length. In spoken form, this time is about 5 times 10 to the minus 44 seconds. This is an interval so brief that it lies far beyond the reach of any current experiment. Yet these scales appear again and again in the equations that combine gravity with quantum mechanics, and they suggest something remarkable. At distances near the Planck length, space-time may no longer behave like a smooth fabric. Instead, it might become turbulent, foamy, restless. Physicist John Wheeler once described this possible structure using the phrase space-time foam. Imagine the surface of the ocean during a storm. From far away, the ocean appears smooth, but as you approach the surface, you begin to see waves, ripples, and bubbles forming and collapsing. Something similar might occur with space-time at extremely tiny distances. On large scales, space-time looks smooth and continuous. Planets move along graceful paths. Light travels in straight lines unless curved by gravity. But if we could zoom into the Planck scale, space-time might appear wildly irregular. Tiny fluctuations in geometry might appear and disappear constantly. Distances might become uncertain. Even the order of events could begin to blur. Quantum mechanics introduces uncertainty into many aspects of nature. Particles do not always have precise positions and velocities at the same time. Instead, their behavior is described by probabilities. If space-time itself becomes subject to quantum fluctuations, then the very stage on which physics unfolds may become uncertain as well. And this is where Einstein's theory encounters a deep difficulty. General relativity treats space-time as a smooth geometric surface. But quantum mechanics suggests that at extremely small scales, smoothness may dissolve into microscopic turbulence. The two theories describe nature with extraordinary accuracy in their own domains, yet when physicists attempt to combine them, the mathematics begins to break down. Equations produce infinities. Predictions become meaningless. It is as if two beautiful maps of reality refuse to align. One map describes gravity and the large-scale structure of the cosmos. The other describes the tiny world of particles and quantum fluctuations. Somewhere near the Planck scale, these two maps must come together. But exactly how they fit remains one of the deepest mysteries in physics. Many physicists now suspect that the true structure of reality at these scales may look nothing like our familiar picture of space-time. Space and time themselves might emerge from something deeper, something more fundamental. And to explore that possibility, scientists have begun searching for new theories that go beyond Einstein's geometry. Theories in which space-time is not the starting point, but the result. A kind of large-scale pattern emerging from deeper microscopic structures. One of the most intriguing ideas in this search comes from quantum physics itself. A theory suggesting that the fabric of space-time might be built from tiny networks of relationships, almost like a cosmic web woven from the smallest threads imaginable. By the time physicists began exploring the mysterious realm of the Planck scale, they were already working with two extraordinarily successful theories. On the one hand, there was Einstein's theory of general relativity. This theory describes gravity as the curvature of space-time. It explains how planets move, how galaxies form, and how black holes warp the surrounding geometry of the universe. On the other hand, there was quantum mechanics. Quantum theory governs the behaviour of atoms, electrons, photons, and the smallest known particles of nature. Both theories are astonishingly accurate. General relativity describes the large-scale structure of the cosmos. Quantum mechanics describes the microscopic world with remarkable precision. Yet when physicists try to combine these two frameworks, they encounter a deep and unsettling problem. The two theories seem to speak very different languages. General relativity describes a smooth geometric spacetime. In this picture, spacetime behaves like a continuous fabric that can bend and curve. Quantum mechanics, however, introduces a fundamental idea known as uncertainty. One of the most famous expressions of this idea is the uncertainty principle. In simple terms, this principle states that certain pairs of physical properties cannot both be known with perfect precision at the same time. For example, the more precisely we measure the position of a particle, the less precisely we can know its motion, and the more precisely we determine its motion, the less precisely we can determine its position. This is not merely a limitation of our measuring instruments, it appears to be a fundamental feature of nature. At extremely small scales, particles do not behave like tiny billiard balls travelling along predictable paths. Instead, they behave more like ripples of probability. Their positions and motions are described by clouds of possible outcomes rather than precise trajectories. Another strange feature of quantum theory is the idea of fluctuations. Even in empty space, quantum mechanics predicts that energy cannot remain perfectly still. Tiny fluctuations constantly appear and disappear. Particles and antiparticles can briefly emerge from the vacuum and then vanish again. These events happen extremely quickly, often within unimaginably small intervals of time. From a distance, empty space appears calm, but if we could observe it at extremely tiny scales, it might look more like a restless sea, a shimmering surface where energy constantly flickers in and out of existence. Now imagine combining this restless quantum vacuum with Einstein's curved spacetime. In general relativity, the geometry of spacetime responds to energy and mass. Energy tells spacetime how to bend. But if energy itself is fluctuating wildly at microscopic scales, then the geometry of spacetime must fluctuate as well. This leads to a startling possibility. At extremely small distances, spacetime may not remain smooth and continuous. Instead, it could become turbulent. Tiny distortions of geometry might appear and disappear constantly. Distances might fluctuate. Even the distinction between space and time might blur. Physicists sometimes imagine spacetime at these scales as a chaotic foam. Small bubbles of geometry forming and collapsing. Microscopic tunnels briefly connecting different regions before vanishing again. These ideas are still highly speculative, but they illustrate the profound challenge physicists face when trying to unify gravity and quantum mechanics. When researchers attempt to apply the mathematical methods of quantum theory directly to Einstein's curved spacetime, the equations often produce infinite results. Certain calculations yield values that grow without limit. These infinities make the predictions meaningless. To deal with similar problems in other areas of quantum physics, scientists use techniques that carefully remove or cancel these infinities. But when gravity enters the picture, those methods no longer work. The mathematics becomes unstable. It is as though the smooth spacetime of Einstein's theory cannot survive the microscopic turbulence predicted by quantum mechanics. This conflict suggests that our current picture of spacetime may not be the deepest layer of reality. Perhaps spacetime is not fundamental at all. Perhaps it is something that emerges from deeper structures, structures that only reveal themselves at extremely small scales. To understand this possibility, physicists have begun searching for new frameworks, theories that do not begin with spacetime as a basic ingredient. Instead, These theories attempt to build spacetime from more primitive elements. Some proposals suggest that spacetime could arise from networks of relationships between fundamental entities. Others suggest that the geometry of spacetime may emerge from patterns of information. Still others imagine that the universe might be built from vibrating strings or discrete loops. Each of these ideas attempts to answer the same question. If spacetime is not the foundation of reality, what lies beneath it? The search for that deeper layer has led physicists into some of the most imaginative territories in modern science. In the next part of our journey, we will explore one of the earliest attempts to construct spacetime from something more fundamental. A theory suggesting that the geometry of the universe might be woven from tiny loops of quantum relationships, almost like an invisible lattice forming the fabric of space itself. After realizing that general relativity and quantum mechanics refuse to merge smoothly, physicists began exploring a radical possibility. What if space-time itself is not continuous? What if space is not infinitely divisible? For centuries, scientists assumed that space could always be divided into smaller and smaller pieces. You could cut a meter into millimeters, millimeters into micrometers, micrometers into nanometers, and in principle continue dividing forever. But some physicists now suspect that this process cannot continue indefinitely. At extremely small scales, near the Planck length, the fabric of space may become discrete, instead of a smooth surface. Space might be made of tiny units, almost like pixels on a digital screen. When you look at a screen from far away, the image appears smooth, but when you move closer and closer, you begin to see the individual pixels that form the picture. Loop quantum gravity is one of the theories exploring this possibility. It suggests that space-time is built from extremely small structures woven together in a network. These structures are sometimes called spin networks, but rather than imagining them as particles, it may be easier to picture them as tiny connections, links in a vast web. Each link represents a small relationship between pieces of quantum geometry. Instead of space existing first and objects sitting inside it, loop quantum gravity proposes something very different. The relationships themselves create space. If enough of these tiny connections combine together, they form the geometry we perceive as space. Distances emerge from how these connections are arranged. Areas and volumes arise from the structure of the network. In this picture, space is not a stage. It is more like a woven fabric made from countless microscopic threads. Each thread represents a fundamental relationship, and together, these threads form the geometry of the universe. One of the fascinating features of a loop quantum gravity is that certain geometric quantities appear to come in discrete units. For example, the area of a surface might not be infinitely divisible. Instead, it could come in tiny increments, small packets of area. The same might be true for volumes of space. Just as energy in quantum physics can appear in discrete amounts, geometry itself might be quantized. This idea is deeply connected to the Planck scale we discussed earlier. Near the Planck length, about 1.6 times 10 to the minus 35 meters, the smooth geometry of space-time may dissolve into this underlying network. At larger scales, the individual links become impossible to detect, just as individual pixels disappear when you step back from a screen. From a distance, the network appears smooth. The geometry of space-time emerges from the collective behavior of countless tiny connections. Another intriguing aspect of loop quantum gravity is how it treats time. In Einstein's theory, space and time combine into space-time, but in loop quantum gravity, time may not exist as a continuous flowing dimension. Instead, time could emerge from changes within the network itself. Events might correspond to transformations in the relationships between these tiny loops. In other words, time may simply describe how the geometry of the network evolves. This idea echoes something that Gottfried Wilhelm Leibniz suggested centuries earlier. Leibniz argued that space and time might not exist independently. Instead, they might arise from relationships between objects. Loop quantum gravity carries this relational idea to an extraordinary level. The geometry of the universe is built entirely from relationships, connections between fundamental elements. Without those connections, there would be no space, no distance, no geometry at all. Another remarkable implication of this theory involves black holes. According to general relativity, black holes contain regions where space-time curvature becomes extreme. The equations predict singularities, points where density becomes infinite, and the laws of physics break down. Loop quantum gravity suggests that these singularities might not actually exist. Instead, the discrete structure of space-time could prevent infinite compression. When space-time reaches its smallest possible units, further collapse may become impossible. Some researchers even speculate that the interior of a black hole might eventually rebound. A kind of quantum bounce replacing the classical singularity. These ideas are still under active investigation. Loop quantum gravity remains a work in progress. Physicists are still exploring its predictions and searching for ways to test them. Yet the theory offers a fascinating possibility. The smooth space-time described by Einstein may not be the deepest layer of reality. Instead, space-time might emerge from an invisible web of quantum relationships, a cosmic fabric woven from loops too small to observe directly. But loop quantum gravity is only one of several approaches attempting to uncover what lies beneath space-time. Another influential theory takes a very different path. Instead of loops and networks, it imagines that the fundamental building blocks of nature are tiny vibrating strings. And from their vibrations, both particles and space-time itself may arise. By the late 20th century, physicists searching for a deeper description of the universe had reached an unsettling conclusion. The smooth space-time of Einstein's theory might not be the final layer of reality, and the discrete networks proposed by loop quantum gravity were not the only possible explanation. Another idea was quietly developing within theoretical physics. An idea that began with a surprisingly simple question. What if the fundamental building blocks of nature are not particles at all? Instead of tiny points with no size, imagine that the basic ingredients of the universe are extremely small, vibrating strings. Not strings like the ones on a musical instrument. These strings would be unimaginably tiny, far smaller than atoms, far smaller even than the smallest particles known in modern physics. In fact, the length of such a string is thought to be close to the Planck length. In spoken form, that distance is about 1.6 times 10 to the minus 35 meters. This is a scale so small that even our most powerful particle accelerators cannot come close to probing it directly. Yet the idea of strings offers an elegant possibility. Different particles might simply be different vibrational patterns of the same underlying string. To picture this idea, imagine a violin string. When the string vibrates in one pattern, it produces one musical note. When it vibrates in a different pattern, it produces another note. The string itself remains the same, only the vibration changes. String theory proposes something similar for the fundamental particles of nature. Electrons, quarks, photons. These might not be distinct objects. They could be different vibrational modes of a single type of fundamental string. Each vibration would correspond to a different particle. Each pattern would carry different properties such as mass or charge. In this picture, the diversity of particles we observe in the universe might arise from the many possible ways a tiny string can vibrate. One of the most intriguing features of string theory is that it naturally includes gravity. When physicists analyze the vibrations of strings mathematically, one particular vibration behaves exactly like the particle believed to carry the gravitational interaction. This hypothetical particle is often called the graviton. Its appearance within the theory suggested something exciting. String theory might provide a way to unite gravity with quantum physics, the long-sought theory of quantum gravity. Yet the mathematics of string theory revealed another surprising feature. For the equations to remain consistent, the universe appears to require more than the 3 familiar dimensions of space. In many versions of the theory, spacetime must contain 10 dimensions. In spoken language, that means 9 dimensions of space and 1 dimension of time. In some variations of the theory, the total number of dimensions rises to 11. At first glance, this sounds almost unbelievable. We experience only 3 spatial directions in everyday life: forward and backward, left and right, up and down. Where could the additional dimensions be hiding? Physicists propose that these extra dimensions might be tightly curled, so small that we cannot easily detect them. To imagine this idea, picture a long garden hose line across a lawn. From far away, the hose appears one-dimensional. It looks like a simple line stretching across the grass. But if you move closer, you discover that the hose has another dimension wrapped around it. An ant crawling along the surface of the hose could move not only forward and backward along its length, but also around its circular surface. From the ant's perspective, 2 dimensions exist, yet from a distance the hose still appears one-dimensional. In string theory, something similar may occur with the extra dimensions of space. They may be curled into incredibly tiny shapes, hidden within every point of the familiar 3-dimensional world. These tiny shapes are sometimes imagined as intricate geometric structures. Their precise form could influence the vibrational patterns of strings, and those vibrations, in turn, would determine the types of particles and forces that appear in the universe. In this way, the geometry of the extra dimensions might shape the laws of physics themselves. Another fascinating implication of string theory is that space-time might not be fundamental. Instead, space-time could emerge from the interactions of strings, just as the smooth surface of a fabric emerges from the weaving of individual threads. In certain versions of the theory, space-time geometry appears to arise from deeper mathematical relationships within the system of strings. The idea is subtle but profound. Space may not be the stage upon which strings vibrate. Rather, the vibrations themselves might generate the structure we perceive as space. This possibility resonates with the relational ideas we encountered earlier in our journey. The notion that space might emerge from relationships rather than existing independently. Despite its elegance, string theory remains incomplete. Physicists are still exploring its predictions and searching for experimental evidence that could confirm or challenge its ideas. The theory describes a vast landscape of possible universes, each corresponding to different shapes of the extra dimensions. Determining which version might describe our own universe remains a major challenge. Yet the theory continues to inspire new ways of thinking about the foundations of reality. And it has led to another remarkable idea, an idea suggesting that the entire 3-dimensional universe we experience might actually be encoded on a distant boundary, almost like a holographic image projected from a lower dimensional surface. In our everyday experience, space feels 3-dimensional. You can move forward or backward, left or right, up or down. These 3 directions appear so obvious that we rarely question them. But in recent decades, physicists exploring black holes and quantum gravity have discovered something deeply surprising. The amount of information that can exist inside a region of space may not depend on its volume. Instead, it may depend only on the area of its boundary. At first, this idea sounds almost impossible. Imagine a large room. Intuitively, we expect the amount of information that can exist inside the room to depend on how much space the room contains. A bigger room should be able to hold more information, more objects, more particles, more possible arrangements. Yet studies of black holes suggested something very different. The story begins with black hole thermodynamics. In the 1970s, physicists began examining the strange properties of black holes. A black hole is a region of space-time where gravity becomes so intense that nothing, not even light, can escape once it crosses a certain boundary. This boundary is called the event horizon. At first, black holes were thought to be simple objects. They were described by only a few basic properties such as mass, rotation, and electric charge. But then physicist Jacob Bekenstein proposed a bold idea. He suggested that black holes might possess entropy. Entropy is a measure of how much information is hidden within a system. In thermodynamics, entropy often reflects the number of possible microscopic arrangements of matter. The higher the entropy, the greater the number of hidden configurations. Stephen Hawking later combined quantum theory with Einstein's general relativity and discovered something extraordinary. Black holes are not completely black. They slowly emit radiation. This phenomenon is now known as Hawking radiation. As a result, black holes gradually lose energy over extremely long periods of time. Eventually, they may even evaporate completely. But Hawking's calculations also confirmed Bekenstein's insight about entropy. The entropy of a black hole is not proportional to its volume. Instead, it is proportional to the surface area of the event horizon. In spoken language, physicists describe this relationship by saying that the entropy of a black hole grows with its surface area rather than with the amount of space inside it. This result was astonishing. It suggested that the maximum amount of information that can exist inside a region of space might depend only on the area surrounding that region, not the volume within it. From this surprising observation emerged a remarkable idea. The holographic principle. The holographic principle proposes that all the information describing a three-dimensional region of space could be encoded on a two-dimensional boundary surrounding that region. To visualize this idea, it helps to think about a hologram. A hologram is a special type of image that can appear three-dimensional, even though it is stored on a flat surface. You may have seen holographic stickers on credit cards or identification documents. When light strikes the surface at different angles, the image appears to have depth. Yet all the information creating that illusion exists on a two-dimensional surface. The holographic principle suggests that something similar might occur in the universe itself. The three-dimensional world we experience could be a projection of information stored on a distant boundary, a boundary with one fewer dimension. In certain models of theoretical physics, this idea becomes mathematically precise. Researchers discovered that a theory describing gravity within a region of space can sometimes be equivalent to a different theory defined on the boundary of that region. In other words, two very different descriptions of the universe may actually contain the same information. One description involves gravity in curved space-time. The other involves quantum particles living on a lower dimensional surface. This surprising connection has become one of the most powerful ideas in modern theoretical physics. It suggests that space-time itself might emerge from patterns of information. Instead of being the fundamental stage of reality, space may arise from deeper informational relationships. In this picture, geometry could be a kind of large-scale illusion, much like the depth you perceive in a hologram. Your brain interprets patterns of light in a way that creates the appearance of three-dimensional structure. Similarly, the universe might interpret patterns of quantum information in a way that creates the appearance of space. Some physicists even speculate that the connections between quantum particles, known as entanglement, might help weave spacetime itself. Entanglement links particles together so that their properties become deeply correlated, even across great distances. These relationships might form a hidden network underlying spacetime geometry. In other words, spacetime could emerge from the relationships between quantum systems. This idea echoes the relational philosophy we encountered earlier in our journey. The notion that space might arise not from an independent container, but from the relationships between objects. From ancient philosophical debates to modern theories of quantum gravity, the same question keeps returning. Is space truly fundamental? Or is it a kind of large-scale pattern emerging from something deeper? The holographic principle does not yet provide a complete answer, but it offers a powerful hint. Perhaps the universe is not built from space first. Perhaps space itself emerges from information. And if that is true, then the familiar three-dimensional world we experience may be only one layer of a much deeper structure, a structure still waiting to be fully understood. For centuries, physicists assumed that space and time were the stage on which all physical processes occur. Even when Einstein reshaped this stage into curved spacetime, the idea remained the same. Events happened somewhere in space and at some moment in time. Coordinates described where and when something occurred. But in recent years, some physicists have begun exploring a surprising possibility. Perhaps spacetime itself is not the starting point of physics. Perhaps it is only a convenient description that appears at large scales. At deeper levels, the universe might operate according to rules that do not mention space or time at all. One of the places where this idea began to appear was in the study of particle collisions. Inside powerful particle accelerators, particles such as protons are smashed together at extremely high energies. When these collisions occur, new particles burst outward in complex patterns. Physicists study these events by calculating something called a scattering amplitude. In simple language, a scattering amplitude describes the probability that a particular set of particles will emerge from a collision. These calculations are extremely complicated. Traditionally, physicists perform them by imagining particles travelling through space-time, interacting through various intermediate steps. Each step is represented by mathematical diagrams showing particles moving, colliding, and exchanging forces. For decades, these calculations required enormous effort, but then researchers discovered something unexpected. The final answers often had far simpler structures than the complicated calculations used to obtain them. It was as though the intermediate steps involving space-time were unnecessarily complex. Some physicists began searching for ways to compute these scattering amplitudes more directly. Eventually, a remarkable discovery emerged. Certain particle interactions could be described using an entirely different geometric object. This object became known as the amplitohedron. The amplitohedron is not a shape that exists within ordinary space. Instead, it lives within a highly abstract mathematical space. Yet its geometry encodes the probabilities of particle interactions. Rather than calculating long chains of interactions through space-time diagrams, physicists can sometimes determine the outcome of a particle collision by studying the geometry of this abstract shape. In other words, the answer appears to come from geometry itself, not from particles moving through space-time. This discovery raised a fascinating possibility. Perhaps space-time is not fundamental. Instead, space-time might be an emergent concept that appears when we describe particle interactions in a certain way. At deeper levels, the universe might be governed by purely geometric relationships. To visualize this idea, imagine trying to describe a landscape using shadows on a wall. The shadows contain useful information about the shapes casting them, but the shadows are not the shapes themselves. Similarly, space-time might be a kind of shadow cast by deeper mathematical structures. When we observe the universe at large scales, those structures appear as the familiar three-dimensional space and flowing time we experience. But at deeper levels, those coordinates may not exist at all. Only relationships remain. This idea echoes themes we've encountered throughout our journey. Leibniz suggested that space might simply be the relationships between objects. Loop quantum gravity describes space as a network of connections. The holographic principle suggests that space-time may emerge from patterns of information. And now the amplitahedron hints that even the calculations describing particle interactions might not require space-time as a starting point. Instead, geometry itself may be the deeper language of nature. Of course, these ideas remain highly theoretical. Physicists are still exploring how these mathematical structures connect with the observable universe. Experiments have not yet confirmed whether space-time truly emerges from such geometric relationships. Yet the possibility is profoundly intriguing. For centuries, we assumed that space and time were the most basic ingredients of reality, the stage upon which everything else unfolds. But modern physics increasingly hints that the stage itself may be constructed from something deeper, something more abstract, a network of relationships, patterns of information, or perhaps pure geometry. And if space-time truly emerges from deeper layers of reality, then our everyday intuition about space may be only an approximation, a useful description that works well at large scales, but not the ultimate foundation of the universe. Yet there is another perspective worth considering. Even if space-time emerges from deeper structures, the way we experience space may also depend on something closer to home: our own minds. The human brain has evolved to interpret sensory signals and construct a coherent picture of the world around us. Perhaps part of our experience of space arises not only from the external universe, but also from the way our brains organize information about that universe. And this possibility leads us into an unexpected direction, one that returns us to a thought proposed centuries ago by Leibniz: the idea that space might partly arise from how observers perceive relationships between objects. Up to this point in our journey, we have explored the possibility that space and time may emerge from deeper layers of physical reality. Loop quantum gravity suggests that space could arise from networks of relationships. String theory imagines tiny vibrating structures underlying particles and forces. The holographic principle proposes that three-dimensional space might be encoded on distant boundaries. And more abstract ideas hint that geometry itself may exist before space-time appears. But there is another perspective that deserves attention, not from physics, from the human mind. Because everything we experience as space is filtered through one remarkable organ: the brain. Every sight you see, every sound you hear, every sensation of movement or distance, all of it must first be processed by neural systems inside your head. Your eyes detect patterns of light. Your ears detect vibrations in the air. Your skin senses pressure and temperature. But none of these signals contain space in the form we experience it. They are simply electrical impulses traveling along nerves. The brain receives these signals and begins an extraordinary process. It constructs a model of the world. From patterns of light falling on the retina, the brain reconstructs shapes, distances, and depth. Two slightly different images arrive from the left and right eyes. The brain compares them to estimate how far away objects are. Shadows help reveal the contours of surfaces. Motion provides clues about distance and size. Even subtle changes in perspective help the brain interpret three-dimensional structure. In other words, the spatial world you experience is not delivered directly by your senses. It is built, constructed. In a sense, your brain is constantly generating a simulation of space, a working model that allows you to move safely through the environment. Neuroscience has revealed specialized regions of the brain dedicated to this task. One of the most fascinating discoveries involves cells known as place cells. These cells were first identified in the hippocampus, a region of the brain deeply involved in memory and navigation. Place cells activate when an animal occupies a particular location in its environment. As the animal moves through space, different place cells become active, forming a kind of internal map. Later discoveries revealed another remarkable type of neuron, grid cells. These cells fire in patterns that form a repeating hexagonal grid as an animal explores its surroundings. Together, place cells and grid cells help the brain construct a spatial coordinate system, not unlike the coordinate grid introduced by René Descartes centuries earlier. But in this case, the grid exists inside the brain. These neural maps allow animals and humans to navigate complex environments. They help us remember where objects are located. They allow us to estimate distances and directions. Yet these maps are not literal copies of the external world. They are interpretations, internal representations, constructed by neural circuits. This realization raises a subtle but intriguing question. If the brain must build a model of space in order to experience it, how much of what we perceive as space belongs to the external universe? And how much belongs to the way our brains organize information? Philosophers have wondered about this question for centuries. Immanuel Kant once suggested that space might be a form of intuition, a framework the mind uses to organize sensory experience. Modern neuroscience does not fully confirm or reject such philosophical ideas, but it does reveal that the brain actively constructs spatial perception. In everyday life, this construction works so smoothly that we rarely notice it. The room around you appears solid and continuous. Objects appear located in stable positions. Distances feel reliable. Yet subtle experiments reveal how flexible this perception can be. For example, visual illusions can distort our sense of depth. Mirrors can trick the brain into interpreting reflected images as real space. Virtual reality systems can create convincing environments that feel spatially real, even though they exist only as patterns of light on screens. In each case, the brain interprets sensory signals and constructs a spatial model. The model can be altered, and sometimes the brain can be persuaded to believe in spaces that are not physically present. None of this means that the external universe is an illusion, but it reminds us that our experience of space is always mediated by perception. The brain translates signals into spatial relationships, and those relationships form the world we consciously experience. Interestingly, this perspective echoes the relational ideas proposed by Leibniz centuries ago. Leibniz argued that space might not exist independently. Instead, space might arise from relationships between objects. Modern neuroscience suggests something complementary. Our experience of space may arise from relationships between sensory, signals, patterns of light, sound, and motion interpreted by the brain. Of course, the universe itself likely possesses its own structure independent of our perception. Planets orbit stars whether or not anyone observes them. Galaxies collide across cosmic distances. Black holes warp spacetime in regions far beyond human awareness. Yet the way we experience these phenomena, how we imagine them spatially, still depends on the models our brains construct. And this realization gently brings us back to the central question of our journey. If modern physics suggests that space-time may emerge from deeper structures, and if neuroscience shows that our experience of space emerges from neural processes, then perhaps the space we perceive is only one layer of reality, a useful representation, a map rather than the territory itself. And with that thought, we are ready to step back and reflect on the remarkable journey we have taken through the history of space and time, / greater than. Throughout this quiet journey, we have slowly peeled back layers of an idea that once seemed obvious. The idea that space and time are the fundamental stage upon which reality unfolds. At first glance, this assumption feels natural. You wake up in a room, you look around, objects occupy positions in space. Moments pass one after another. Your day unfolds through time. Space feels like the container that holds the world. Time feels like the river that carries events forward. For centuries, this simple picture guided human thinking. Isaac Newton imagined the universe unfolding within a vast invisible framework. Absolute space provided a fixed arena. Absolute time ticked forward uniformly, like a cosmic clock that never paused. Even if nothing happened, time would continue flowing. Even if all objects vanished, space would still exist. This picture proved incredibly powerful. Newton's laws of motion described the movement of planets with astonishing precision. The pairs of comets, the fall of apples, the swing of pendulums, all could be predicted with remarkable accuracy. The universe appeared to obey elegant mathematical rules operating within this stable framework. Yet philosophy never fully accepted this picture without question. Gottfried Wilhelm Leibniz proposed a different vision. In his view, space was not a container. It was simply the set of relationships between objects. If all objects disappeared, there would be no distances to measure. Without relationships, space itself would have no meaning. At the time, this debate remained largely philosophical. But in the 20th century, physics began reshaping the discussion. Albert Einstein introduced a profound shift. In special relativity, space and time were woven together into a single structure called spacetime. Distances and durations depended on motion. Clocks ticked at different rates for observers moving relative to one another. Length contracted as speeds approached the speed of light. And then, general relativity revealed something even more extraordinary. Mass and energy do not simply move through space-time, they shape it. Gravity emerges from the curvature of space-time itself. Massive objects bend the geometry of the universe. Planets follow curved paths not because an invisible force pulls them inward, but because space-time itself is curved. For a time, this idea seemed to elevate space-time to the most fundamental structure of reality. Space and time were no longer passive backgrounds. They were dynamic participants in the cosmic story. Yet even Einstein suspected that this picture might not be the final one. When quantum mechanics entered the scene, a deep conflict appeared. General relativity describes smooth, continuous space-time. Quantum theory describes a universe governed by probabilities and discrete interactions. When physicists attempt to combine these two theories at extremely small scales, the mathematics begins to break down. Near the smallest measurable length, roughly 1.6 times 10 to the minus 35 meters, the smooth fabric of space-time may no longer make sense. Instead of a calm geometric surface, the universe may become turbulent and uncertain, a region sometimes described as quantum foam. To understand this realm, physicists have explored many possible ideas. Loop quantum gravity suggests that space may consist of tiny interconnected loops. String theory proposes that particles arise from minute vibrating strings existing in additional dimensions beyond the familiar 3 dimensions of space. The holographic principle suggests that 3-dimensional space may emerge from information encoded on distant surfaces, and geometric structures such as the amplituhedron hint that particle interactions may be described without referencing space-time at all. Each of these ideas points toward the same intriguing possibility. Space-time might not be the foundation of reality. It may be an emergent structure, something that appears at large scales when deeper relationships organize themselves in particular ways. This idea is not entirely unfamiliar. In everyday life, many properties emerge from simpler ingredients. Temperature, for example, emerges from the collective motion of countless atoms. A single atom does not possess temperature, but a large group of atoms moving together produces the sensation we describe as warmth or cold. Similarly, the smooth surface of a lake emerges from the collective motion of countless molecules. Up close, the water is composed of individual particles moving in complex patterns, but from a distance, it appears calm and continuous. Space-time may behave in a similar way. At large scales, the universe appears smooth. Distances stretch across galaxies. Time flows steadily forward. But at deeper levels, the universe may consist of networks, vibrations, or patterns of information whose collective behavior produces the space-time we experience. Even our own perception of space reflects this layered structure. Neuroscience shows that the brain constructs internal maps of the environment. Cells within the hippocampus fire in patterns that help us navigate through rooms and landscapes. The spatial world we experience is partly a model assembled by the brain, a practical representation that helps us move through the world. In this sense, our experience of space arises from relationships between sensory signals, memories, and neural activity. And so the journey we began with ancient philosophy comes full circle. The debate between absolute space and relational space continues today, not only in philosophy but in cutting-edge physics. Is space-time the deepest structure of the universe? Or is it a remarkable illusion that emerges from deeper patterns? For now, the answer remains uncertain. Yet uncertainty is not a failure of science. It is an invitation to continue exploring the hidden layers of reality. And perhaps that is the most beautiful aspect of this story. The deeper we look into the universe, the more it reveals structures that challenge our intuition. Concepts that once seemed solid begin to soften. Foundations become possibilities. Space and time themselves, once thought to be the unchanging stage of existence, may turn out to be part of a much deeper narrative, a narrative still unfolding. And as we step back from these ideas, it becomes comforting to remember that the universe has always been richer and stranger than our first impressions suggest. Whether space-time is fundamental or emergent, the cosmos continues its quiet dance of galaxies, stars, and atoms. And somewhere within that vast unfolding story, curious minds continue to ask gentle questions about the nature of reality. Questions that lead us, slowly and patiently, toward deeper understanding.